So we're going to look at section 3.3 today, and this section's got a lot of stuff in it. It can kind of get all over the place, so I'm going to try to break it down as best as possible. The first thing they go into is something called a z-score. Now, the way z-scores work is we're going to actually measure how far data is from the mean value. So that might not seem terribly interesting, but the idea is that we want to come up with kind of a universal measure, a special measure. So let's say we have our data, something like this, and we find the mean. We call that x bar. So we add up all the data values, and we divide by how many data values there are. Well, there happens to be 3 in this case, 1, 2, 3. So we get 6 over 3, or 2. So x bar is 2. And so what we want to do is we want to measure how far these data values are from the mean of 2. Well, I mean, that doesn't seem terribly hard here. I mean, take a look at this. So we have let's put our data on a number line. 1, here's 2, which is also our x bar. Here's 3. Well, 1 is a distance of 1. 3 is also a distance of 1, and 2 is a distance of 0. So there we go, we got the distance. Well, what we want to do instead is compute a distance using standard deviations. Instead of saying, well, 1 is 1 unit away from the mean, or 3 is 1 unit away from the mean, which is certainly true, we want to talk about how many standard deviations away is each data value. And that's what z-scores tell us. I'm going to abbreviate standard deviation as SD. So how many standard deviations each data value is from the mean? And again, the mean we call x bar. Now remember, the median, we gave that a little curly Q there, a little curly there, that's going to be our median. This is our mean x bar. So the idea of a z-score, and the way they present it using population means and population standard deviations. In practice, the z-score for any value x is we subtract the mean that we compute divided by the standard deviation. And so we convert our x value into a z-score. So if you had our first x value, call that x1, we get the z1. So instead of reporting our x1, we would say, well, we have z1 instead. And if we have, say, z8, well, where did we get z8? Well, that had to be the 8th data piece divided by, well, there you go, you subtract the mean, divide by that same standard deviation. So this would be the z representation of this data value. And we'll do an example here. So there's some advantages to this. For one, z-scores have no units. And it's a way of comparing different types of data sets. Like you have temperature over here, and then maybe we have wind speed over here. And we can convert all of our data into z-scores, and we can compare z-scores. So we can compare data sets, not of the raw data, but of the raw data converted to z-scores, if we wanted to do that for some reason. And again, it tells us, each z-score tells us how many standard deviations away a particular piece of data is from the mean. So we typically see this represented in another way. And it's usually using a data or a datum minus the population mean divided by the population standard deviation. And again, these are sort of ideal things that really we don't usually have access to. So we'll just go with it. We'll go with the other one in practice. All right. Typically with z-scores, we round to 2 decimal spaces, or no, places. And we do this for z-tables. We're going to talk about later. And this is sort of a general thing they mention. Z-values, we'll talk about significant values or significant data values. And typically, when we have something that's significant or it's pretty far from the mean, the idea is the mean is kind of what we expect. And then the farther out you are from the mean, well, this is kind of unusual. So we're going to have a significantly you have a significantly low z-score if your z-score is less than -2. For significantly high, you have your z-score greater than +2. So, and we'll get into more of this later when we talk about z-tables and hypothesis testing. We're just sort of introducing it. Probably what comes up in this section is that this is the chapter where we learn about means and we learn about standard deviations. Well, this is where we use the mean x-bar along with the standard deviation s and put it to some use, though we're going to get into more of what this use is later. We can compute z-scores, but other than comparing different data sets for some reason, what do we do with them? Well, that's for future endeavors. So moving on. So the last thing to mention about z-scores, I just want to go through an example. Now, throughout this section, I'm going to be referring to a data set. It's table 3-4 on page 115. Now, you don't have to actually look at this data set to do this. You can follow along the examples, but if it helps, go ahead, take a look at it, and you can see what I'm talking about. But you won't really absolutely have to use it. All right. So let's say we have this. Well, here I'm going to do a slightly different example. So we won't need this data set just yet. But let's say we have this. Let's say we're looking at newborn weights. So we have a bunch of newborn babies, and we need to get a mean weight for them and a standard deviation. So the mean, x bar, let's say the average weight is 3,152 grams. And then the standard deviation, and again, we're using those formulas from last time. Standard deviation is 693.4 grams. So we might be asking a question. Let's say a newborn is 4,000 grams. Let's convert this to a z-score. So the z will be the data value itself, that's x, minus x bar. And here I'll write out the formula. So 4,000 minus 3,152 divided by 693.4. And we do that, what we're going to get is about 1.22 or 1.22. And that's our z-score. And that's it. So what we can do, instead of maybe working with this data value of 4,000 grams, we might work with the z-score. And what this says this data, this piece of data, is 1.22 standard deviations above the mean. And so that's your z-scores. So if you have any questions about that, let me know.